Can you guys hear me? Should be fine. Okay. So yeah, today I'm going to talk you through some of the methods for distribution shift. So first of all, try to motivate this problem. I think Professor also mentioned this in earlier lectures, like why we should be careful in reality and why this ideal assumption is not always the case in reality when we do machine learning, try to apply machine learning in some of the applications. So in traditional machine learning, we assume the data distribution is the same between the training data and test data. Or for example, in the MNIST case, if you have some benchmark data set as MNIST and you collect a lot of the data of human handwriting and of the digits, and then when we try to test our algorithm, usually we also have we just withheld a portion of the data from the same pool of data. So that means the test data is actually the same has the same distribution as the training data, or its ID distributed as the training data. So that's why in those cases we can get good guarantees. Also in theory, like we can prove that our algorithm has generalization bounds. That's all under the same assumption that training and testing, they are the same distribution, their ID. But in reality, what will happen is, for example, you see in many, we have many very large benchmark data set, but even though we have those data set, it can be sometimes you need to apply on some domain that's the benchmark data does not cover. For example, you want to train from MNIST those digits that they are human handwritten very clearly under some under some experiments, but then you want to predict maybe this is the SVHN data, which is the door sign. Like we want to recognize what's the signs on street or what's the signs on the people's doors. And then they are not human written digits, but they are digits. So there are some similarity between these two, and then but maybe it doesn't make much sense to directly just train some predictor from this data, from this MNIST clean one to someone that's much more blurry, and then it's collected in the wild, collected online, and then maybe collected on the street. So in this case, we call it source and target. In domain adaptation literature, usually you have source and target. All you can say is train and test. It's interchangeable. It's fine. It's just say the source one joint distribution of x, y is different with the target joint distribution of x, y.
So how many of you have worked on domain adaptation or in applications found that there's significant distributional shift? How many of you have? In what context?
In the environment in which we're collecting data from, it just didn't represent all the environments we would in the future collect data from or test on. So we had to essentially the study was a kitchen. And so we collected data from doing a pose estimation for different objects in the kitchen. Mm-hmm. And so our data would fit to our kitchen's background, to our specific objects in our kitchen. But we needed to represent all the kitchens, possibly in the US. And so that's a case where it had it was a good subset, but it was not at all a representation of what the test would be like.
Yeah, and I think in reality it's very hard to cover everything, right? Especially in those applications like self-driving cars, then all the extreme cases it's very hard to cover in all your training data, to cover all the extreme cases. What's the people crossing the road, and then different extreme cases. So, yeah.
It sounds like here it was like now new categories appearing, but the original was the same, right? So it sounded like it was a subset of the.
It was a subset, but it was also a shift in that we only had one model to work with. Mm-hmm. For example, there are different models of friars, and our model is just one model, so we couldn't represent the other models. That's a significant possible change that we weren't sure how to, model or adapt to.
And maybe after she introduces the techniques, you can comment on what you used and what worked right in the end. We should.
Sure. Yeah, we should come back and ask you what's the techniques you're using there. Yeah.
What about others?
So how do you know if you have distribution shift?
Yeah. So this is a good.
You just look at this and see if it's different.
Right. Right. The shift detection is also one literature. We'll review some of the method for how to define, how to detect whether there's a shift or not. So this is also one important problem under this distribution shift topic. Yeah. Okay. So before I dive into the details of the method, I want to give you a very general view of two perspectives of doing machine learning in general. And then we'll first just give you this idea, and then we'll have different examples of these two perspectives, in general perspectives, later in this talk. But yeah, I want to first give you this overview, and you can keep in mind there's two threaded work we'll be talking about. So the first one is empirical risk minimization. I think it's covered in previous talks as well. So it's a very straightforward and very popular and also principled way of doing machine learning. So you have some risk function that a loss function is defined for some of the f is, for example, is some predictor function, and maybe y is the true values, and then you have some loss function defined on this, and then you want to minimize this loss function under some distribution, but you do not have this true distribution. You only have some samples from this pxy. For example, pxy is your population, is your true distribution. Then you have some samples. We use p tilde here as this empirical distribution. Then so you want to minimize this loss, expected loss under this empirical distribution. And usually f is in a restricted set because you really want to avoid overfitting. We want to add regularization, we want to constrain our set of function class. So in a restricted function class, we want to minimize some expected loss function under some empirical data distribution. So this is what we want to do in empirical risk minimization. So this is one big class of methods in machine learning. So another class of method we call the minimax approach, or there actually are different names, like robust estimation, or like gamma robust, or robust Bayes. So in this case, I just call it a minimax approach. And then it's kind of different perspective from the empirical risk, the first one. Here we still have this loss function defined on some defined as the risk we get from some f predictor, which we want to learn, and also some true maybe true y values. But then we have this pxy, which is the true distribution here, and this is not a true distribution. It's just a certain distribution pxy. And then this pxy is actually proposed by some adversarial player or some max player in this game. So this pxy is in this set. So we're saying, okay, this pxy is in a set. We can have different constraints of this set. It's just a set, and then you just draw some distribution from this set. And then another player is f, which is our predictor, and this predictor tries to minimize this loss. So there are two players in this game. One is our predictor player wants to minimize this loss, expected loss function. Another player is this p player, which is a max player, and this defines our distribution. We want to do this expectation of this loss. So the difference between the first one and this one is like, now our f is not restricted in this function class. So f is actually free now, but then this p is restricted in a set. So this distribution is restricted in a set. So this is the two. Just keep this in mind, and then we'll remind you about this thing later in this talk. But this is the second general perspective we want to mention in this, and we call that minimax approach.
So the special case of minimax was the robust learning we covered, right? Because there we are perturbing the input,
right,
and we are optimizing over it. So it's a very special class of
right,
how you're constraining the space of the distribution.
Right. In the robust learning talk we had before, this So there are different ways we want to restrict this P. So it can be, in our talk today, we'll talk about how we restrict the P conditional label distribution, which is the Py given X. But in the robust learning case, you can also say, okay, this P is on this X, so the Px is different, and you have perturbations on this input variable, which is the X. So there are different ways you can do this, constrain this P. But yeah, in general, it can be just on this joint distribution. And you have a restricted set of P. So there's a difference. Instead of constraining the space of F, you're constraining the space of P. Okay? Any questions? Yeah.
Why is the, I mean, in principle, one could just as well have constraints on the space in which F lives.
Yeah.
The second case, right? So why is it so that when we start putting the constraints on P, we drop any constraints on F?
So there's still constraints on F. I guess you just.
There still can be, but in general, it can be nothing. There's one special case that so it still can be constraints on F. But in the more general case, I would say which one is more general. Maybe I should put the constraint here. But it can be like nothing. It can be in a free play as a free player in this case. Yeah, I just want to mention.
There's nothing special changing between the two.
Yeah, that's what
it's the same.
Yeah, and since in this talk, all the formulation I had, there's no constraint in F. But in reality, yeah, you can still also have constraints on F. Yeah. Any other questions? Cool. So the roadmap of this talk is, so we introduced ID versus distribution shift. We introduced the two perspectives. One is empirical rationalization, and one is minimax approach, as I said in the previous slide. And I make this table. So there are different methods in different cells in this table. So you can do ID, and then you can do ERM, and then you get all this traditional regression, SVM, boosting. So they are actually doing different loss minimization in the ID case. And then in the distribution shift case, and if you are under this ERM framework, you end up with impulse weighting formulation. And then we will cover how about in the covariance shift case, how do you do impulse weighting, and also in the label shift case, how do you do impulse weighting. And also I'll cover in the ID case, there are certain special cases when these two formulation is exactly the same thing. So in the log loss case, the ERM formulation will be exactly the same as this minimax approach formulation. But there are other cases when they are very different. So we'll talk a little bit about that. And then in the distribution shift case, if you're in the minimax approach framework, then you'll end up with this robust bias web prediction, which we'll call robust prediction. So it's an alternative of methods of doing impulse weighting under distribution shift. So we'll cover these four set of things. Any questions? Yeah.
Pause my slide for a second.
I'm sorry?
Please pause my slide for a second first.
There is
He's just saying pause first.
Okay. Let's see. So, okay, first let's recap the ERM framework. So as I covered a little bit before, so you have some loss function defined, and then you have population, Pxy, and then F is constrained in the function class. And then since we do not have the true distribution of joint distribution xy, we use the samples to approximate this distribution. So then eventually you get this, you're minimizing the mean of this, maybe you have M samples, then you just have this mean of this empirical loss functions, and then you minimize that. So this is the standard way. And as I mentioned, in this loss function, in classification, usually you care about 0-1 loss, which is like if you misclassify one example, you suffer one loss. But this loss cannot be efficiently minimized under this framework. So, and it's not smooth. So people developed a different surrogate, convex surrogate of 0-1 loss. So you can have log loss, then you get logistic regression in that case. If you have hinge loss, then you get SVM. If you have, I think exponential loss, if you have exponential loss, is certain version of boosting method. So people try to use different upper bound, different convex upper bound of 0-1 loss to plug into this empirical risk minimization framework, and then get different powerful classifiers. Any question? Okay. So this is the way we do ERM. And then in the imbalance weighting case, when we have these different source and target distributions, one of the easiest thing we can do is reweight our examples in this ERM framework. So you can see that still it's very similar. We have some source empirical distribution there. We have loss function here. Maybe you can also prescribe it as some theta parameters. And then if you weight, you have some kind of weight of p target xy, which is the joint distribution, and p source xy. If you know that, then asymptotically, if you are sample everywhere in your source distribution, and then and you have an infinite number of samples in your source distribution, then these two will cancel out. Then this will just give you the expected target loss. In this case, the point of interest of loss function is on the target distribution. And then in this way, we kind of use sourced samples, but using a reweights weights on each of the samples, we end up with asymptotically the unbiased target loss function. And that's kind of, this is where we can get our goal. And now the problem will just reduce to how do you get this kind of weights? If you can get accurate weights, then yeah, problem solved. You get your target loss function minimized instead of the source one. Any questions here? Cool. So depending on what kind of shift you have, this problem can be, imbalance weighting can be reduced to different formulations. For example, if we have a shift only in the x, which is the input variable, then it's called covariance shift, where the assumption is the shift, it only happens in the x variable, which is the input variable. P source is not equals to p target x. However, the y given x, the conditional label distribution, is still the same. So this is kind of, you want to decompose your joint distribution to px and the py given x, and just assume the shift is only in px, not in py given x. And the other case is the opposite, which is the shift is only happens in the label or y variable, but not in the x given y distribution. So you find another way to decompose your joint distribution pxy. You have y py and then px given y, and then shift only happens in the labels or in the y variables, but this x given y is the same. So these are two ways to further assume, make some assumptions, say not in general, but we have some specific assumptions about where the shift happened. And then the first case will be more suitable when, for example, you have some function that's universally between this source and target distribution is universally defining your decision boundary, but you only have, because you have sample bias, then you can only sample a portion of the data and not sample the other. So, but still the function class, this function that define your decision boundary or define your this relation between x and y is still the same between the source and target. And in the label shift case, it's more suitable for the situations. For example, in the clinical applications, you want to predict a disease given the symptoms. But then usually, given the disease, the symptoms distributions is usually the same. It's that you have different disease distributions when you maybe sample data from different time period of the time or from different locations of the country. It's the disease distribution is not the same. But given the disease, the symptoms usually is similar. Then this usually is the label shift case. So it depends on what kind of problem you have, what kind of applications you have. You may make different assumptions. We'll choose one of them that's maybe closer to your reality. Yeah.
Can people think of examples of either cases? And of course, there are many that don't fit any of this, right? It could be a mix. But can you think of examples that where this would be a good approximation, either the covariate or the label shift? I mean, Andrew gave 1 or 2 examples, right? But do you think there are other good examples?
Let's say you're trying to classify a data set of dogs as dogs and you're just Dalmatians, but then you have a larger data set with other breeds of dogs. So the label is still the same, but the training set does not represent, the training code variance doesn't represent the test code variance.
Yeah.
And so in that case, the source and target are certainly not the same distribution, right? But why do you think the second assumption is fairly true?
This as in the P source Y given X.
Yeah.
Because no matter what, you're still predicting the same label, which is that you're looking at a dog. So I believe that even if the covariates are different, the labels will still always be the same. Is that true?
Right, so I guess the way, given like an input, how the label is generated is, I mean, you know, what you've said is also an extreme case, right? Maybe it's not singular, I mean, it's singular, then it kind of becomes also degenerated. We can't precisely have that, right? On the other hand, say mostly Dalmatians and then a few, you know, other breeds, right? So in that case, I mean, the question is like what changes between the two, right? If you look at the second one, then P of X given Y is the same. So there, in saying given a breed, right, which is the category, then how the overall distribution is pretty much the same. Right? It's just the proportions of the breeds change. So it's more the label shift case than the covariate shift. Right? So it's the, you know, if you assume the generative model in which the samples are generated given the category is the same, right? Then it's the label shift. So in the first one, I think the more, I think an example of that would be like where you wanted to classify dogs versus cats, but now in the training there were mostly Dalmatians and few of the other breeds, but in the testing it was more of the, like say, Labrador and less of the others. Right, so the distribution is changing. So it depends on what you call the label or what you call the input. Right, so think of it as in the first one, there are many latent attributes within X. Right, so think of it, it could be subcategories, but you haven't labeled that. And if those proportions change, then that's one special case of covariate shift, because the density of X has changed between the two. But on the other hand, you know, what you call a dog hasn't changed, right? Like, so the probability, you know, as long as none of those dog breeds are mistaken for cat, right? If that kind of remains the same, then it's still a dog, right? So, so their P of Y given X is fixed. On the other hand, if you're like, you know, if you have labeled samples of different breeds, and now these proportions change, then it's more like the label shift case. Right?
Yeah.
Does that make sense? I think within the same example, you see how, depending on where the labels were available, the you know, whether it was covariate or label shift changed. Is that distinction clear? And in general, it could be a mix of the two, right? So you could have like, let's say the proportion of both cats and dogs change, but even within the cats and dogs, the subbreeds, the breeds and the subcategories also change, right? Then it's like a mix of both. I mean, the reason we make this distinction is under these special assumptions, you could have simpler algorithms, right? But in many cases, it may not satisfy, and it's a much harder case.
Yeah, for the first case, for example, I have an example, I'm not sure whether it is correct. For example, we take pictures both horizontally and vertically, right? We train model horizontally and we have a kind of model, right? But if we try to use vertical kind of vision one, doesn't mean that we have different source distribution, but the P and Y comma X is the same.
What is the Y variable here?
The Y, for example, the thing you take, whether
The object.
whether you take is a cat or dog.
Okay.
I mean, that is covariance shift, right? Because, how you label based on the input didn't change, whether it was vertical or horizontal.
So I think from this, whether it's X generate Y or is Y generate X. Like in the clinical case, it's disease generates this symptoms, but in the image classification case is given this image, you generate these labels.
I mean, in image classification, it
can be
entirely true. I mean, causality is a special case. Again, if it's causal, then you can immediately infer, right? What if X caused Y or Y caused X? It's clear which one of the two it will be, because if that causation model is fixed, then whichever distribution you change, right, will be the shift. For instance, in the label shift, it's like the category Y is like leading to generating X, right? So so like these diseases lead to symptoms, right? Not the other way. But that's a special case. You don't need to have a causal mechanism for this, right? Whereas in image classification, it's less clear because there are, as I said, both. The labels, the categories which you label, they may change, right? But then there's so much you don't label. There is these latent attributes. Even if that changes, then your P Y given X also changes, right? Because, so it depends on what changes there, right? So, or even P X given Y could change because, the proportion of like different breeds of dogs you had, right? That's P of X given Y. Changed from one distribution to another, right? So then you have, it's no longer the label shift. So in general, like if you just look at arbitrary image classification of two sets and different, it may be a mix of the two, right? You can't immediately say it's one or the other. Any other questions here?
Yeah, I'm sorry, I may be way off base here, but does this only apply to classification? It applies to regression as well?
Regression as well, yeah. We'll actually give examples of regression. So it's, in general, supervised learning, so this is not just classification, but we take classification as the example, and then, but it should method, like this importance weighting, actually is first proposed in the regression case. And then, so both. Okay. So depending on where this shift happens, is in covariant or is in label, then this weight estimation problem will just reduce to, because see some part of this joint distribution cancel out between this source and target because they're equivalent. Then this, in the covariant shift case, then this weight estimation will just reduce this P target X over P source X, so on the X variable. In the label shift case, then is just reduced to P target Y and then P source Y. So just the one single variable. So things will be easier. That's why we first want to make those assumptions. Then we got this only one weight estimation only related to only one variable. Then things get easier. So in terms of the ways to do weight estimation, actually there are many research in this. So here I just list some of them. So in the covariance shift case, actually the research is richer. In this case, we can do KD, we can do discriminative models, we can do KMM, and then we can also do some of the post-processing after you get dense estimation. And then in the label shift case, we can also call this a class ratio estimation. Usually, you want to estimate these class ratios because in this, for example, in this label shift case, you have 10 classes. Then this p target y is just how in the 10, you have a maybe 10-dimensional vector, which is the distribution of how many examples are there in each of the labels, and then this is exactly just how you want to get these class ratios between the source and target estimated. And then we'll introduce one of our recent method using the black box classifier. So first, let's take a look under covariance shift. So there are many research in this. The first perspective is that you can first do dense estimation, and then do this divide do this ratio thing. So dense estimation is also a very broad research area, and then one easiest thing you can do in low dimensional, you can do current dense estimation, and then there are a lot of other things. We will not talk about this today. So this is like you first do dense estimation directly. That's using a bunch of source data, and then you want to figure out a function, a dense function, so that you can, given new data, you can give the likelihood whether this, how likely this data is it belongs to this source distribution, right? And then you first do this for both source and target, and then you can do a divide thing. And another thing we'll talk more about today is direct density ratio estimation. So instead of first do density estimation and do divide, we can directly do this density ratio estimation using, we'll talk about two methods today. One is called probabilistic classification, one is called moment matching, which is KMM. And then there are also other methods in this category too. So in probabilistic classification, which is actually a very simple idea. So you have data from source, and you have some samples from target. And then whether you can use a classifier to classify these two, to figure out whether some data is from, how likely it's from training or how likely it's from testing, how likely it's from source or target. And then the idea behind this is actually the Bayes rule. So according to this derivation, we can say that this density ratio, we use denominator and numerator in this, since I borrowed the slides from Professor Tsujiyama. So just bear with me. Instead of source target, we'll just say one is numerator and one is denominator and one is numerator. And then this ratio between these two will just reduce to a ratio of P. This is like just how many data are there in the source or in the target. And this is just given X, whether it's from this distribution or distribution. So this ratio will just reduce to first get this class ratio, like how many samples you have from either source or target. And then this is just the classification. You can easily get from some classifier, some probabilistic classifier especially, to say, given this X, what's the probability is from this distribution or from the other distribution.
And did you want to explain the intuition of why you're dividing it into these parts?
Why we're dividing into these parts?
What's the advantage of, like, decomposing the numerator and denominator into these?
Oh, so the Bayes rule?
I mean, or why do it this way, right? What is the intuition behind having this conditional distribution of the numerator given X?
I mean, this step, is that? So, let me see. So this is clear. This ratio is equals to this thing is clear, and then it equals to this. I think it's kind of intuitive because this actually just says what's the probability of X in this source distribution, and then
And the second one, right, like what is so the P of denominator given P of numerator, then you can directly compute.
Right.
So how many samples are in denominator and numerator, or the source or the target, that's direct. But the posterior of inferring whether a sample came from source or the target, right, what is the intuition of using that?
You mean this part? Oh, this whole formula is derived from this. And if you write out the base rule, let's maybe do a derivation.
No, what I meant was, the intuition here is that, if you can't distinguish a sample if it came from the source or the target, that means that's kind of the common ground, right? So they would whereas the ones where you can easily distinguish that this was target, this was source, those would be the interesting one. Those would contribute to the ratio, right? Otherwise the ratio would be 1. And so here it's kind of directly going at that posterior.
Yeah.
Right, because you're trying to infer, given a sample, can I say, map it back to the source or the target, right? What is the probability in the source, what's the probability in the target? If those two are the same, then that sample is not interesting, right? So for that, the ratio is just merely 1. So thinking of the posterior makes it kind of more natural to look at what would be samples that distinguish the source and target and what are the ones that are the same. Does that make sense? Right, the base rule is, I guess, clear, right?
Yeah.
The intuition of how through the posterior you can make this distinction of, whether it came from the source and target, can you easily distinguish using this sample? Those would be the samples you really care about.
So if the ratio is pretty high or pretty low,
then
we say that this sample is representative.
The sample it's important, right? Because the rate, it's going to change, on those samples, you don't want to directly apply your classifier. That's when the reweighting is important.
Yeah.
This is kind of taking an inferential viewpoint, right? Like using this sample, can you easily tell whether it came from source or target? Like those are the samples where reweighting would be needed, and that kind of shows up here. And the other thing you want to account for, the source and the target have different number of samples, so you want to also incorporate that.
Any other questions?
Because now you can see how you could implement it, right? If you had a discriminator that tries to discriminate whether the sample came from the source or the target, right? That's when you can compute this ratio.
Yeah. So this just makes things easier to say, okay, we just train a classic discriminator model to try to differentiate whether things are from target or from source too. So just label some source data as 1 and label some target as -1, as positive one or negative, and then do a binary classification, train a binary classification from this 2 sets of samples. And then you also have something that you can predict. For example, then you get a new x from somewhere, and you can also just compute this ratio by doing a prediction using this classifier and get these 2 values from this classifier and do this computation, get the density ratio.
And here we assume px are the same. No problem.
Okay.
You're looking at the ratio of the px, right? And this is the covariance shift, so px is different.
Yeah. So in the covariance shift case, we canceled out the y given x part, so we only have px there.
Yeah, so we cancel y given x. Is y given x the p numerator given x? Is that py given x? Or?
Oh, so then there's 2 things, right? So the previous one will have py given x. That's the real labels. That's for example, it's it's maybe some sample from amnis or some samples from the door sciences. These are actually the digits. But then here, this y, this little y, is the label of whether it's source or target. It's different. It's a positive, negative. So this y is this is not the same labels as the original one you have in your original problem. This is kind of sub-problem. You first do a classification on the source and target distribution, do a binary classification, and then after you get your samples, you do impulse weighting. You apply. So the second step is you apply those weights to the whatever originally probably you want to do neural network on this digit classification. Then you just apply those weights on those samples, but still using your maybe the previous models you have.
So how to label whether X is from the source or the target?
How to label like the source and target? So in this case, for example, we assume we will have some samples from source and also have some samples from target.
Overlap position.
I'm sorry?
The overlap position.
They can overlap. We're not assuming they're disjoint. So in this case, we want to be general. So it can be maybe the source and target they actually overlap. And actually, this is the most cases we look at. So they should have some overlapping. Otherwise, it's hard to learn things from those things. If they're totally disjoint, then it's very hard to learn. It's kind of hopeless. So. So in this, I want to mention one of the assumptions is we assume we have labeled samples from source, but we only have unlabeled samples from target. That means we do not have the y's. We only have the x's. So then we can use the both x to do the classification. Okay. So I think the next slide is an example. Of this thing. So the example is like you have probably two Gaussians. The one is the source and one has in the left top figures. And then since this Gaussian get the two densities, and then they choose a kernel logistic regression with Gaussian kernels as the discriminative model for classify whether it's source or target. So then you have two Gaussians, and then you have labels. One is source, one is target, and then you train a kernel logistic regression with Gaussian kernels. And then you apply things back, and you get, you look at what's the true ratio, because the true ratio is from the true densities you can easily get. And then compare with the estimated ratio, which is from this classification problem, and then try to align these two, and then it works well in this very small problem. So this is an example. Like you can also, if you're interested, you can also try something like that in after class. Right? You have two Gaussians, and then it's very easy. And then you train a classification, and then apply back to see whether the true using this weight estimated in this way versus the true densities, whether they match or not. So as a summary, the good thing for this method is you can use any probabilistic classification method you have. You can use off-the-shelf software, and then it's also there's some theoretical properties that's proved that is asymptotic. Achieve the minimum asymptotic variance for the correctly specified model. So still, if you have misspecified model, you can get problems. And then you can also extend this to multi-class classification. For example, you have three distribution, not two. So instead of doing a binary classification, you can do multi-class, and then still follow this idea to get the density ratios for multiple densities.
Do you want to expand on what you mean by not reliable on misspecified models?
So here, they choose kernel logistic regression with Gaussian kernels, which is good. So you have a universal kernels, and then and also it matches with your original dish data, right? You have two Gaussians. So I think in general, it's hard to, for example, you have just some real data, and then it's hard to say what to pick. Okay, you want to pick logistic regression, or you want to pick some other probabilistic models to do this classification. It can be, it does not match well with the data. So so that means you do not always have this aligned that well in reality, right? And this is just a Gaussian case, which is very easy.
And especially in high dimensions, right?
Right.
So how you estimate the density is hard.
Right, right. And I want to have one comment because I use this also in my research. So when you train this classification, you can also, for example, do different level of regularization where you have very high dimensional, and then it can be very sensitive to some small difference in the data, and which you do not actually want in your classification.
It's not stable.
It's not stable. So, so this is in theory very nice, but it also requires something. Requires for example, have a good model, and requires this good model you've trained well, and then requires the dimensionality. You do not suffer like crystal dimensionality when you do this. So they also have the restrictions of this method. Any more questions before we? Okay. So, so the second method to do direct density ratio estimation is do moment matching. So the idea is you want to, so look at this formulation. You have some distribution of source and distribution target, and then you finally want to match. Like after this reweight, actually you want this expectation. This actually is the expectation of x, and then equals to the expectation of this distribution. So after reweighting applies to maybe one of the distribution, then the expectation of the data should match with the source one. So if this is target and this is source, then after reweighting, this should match the expectation of the source data. So this is actually from the impulse weighting idea, right? After weighting, you want to this source cancel out and then get the target. And in this case, it is like after weighting, you want the data distribution expected of x will match with the expected x under the source distribution. So, but the problem is if you only match a finite number of moments, so the data here is not just maybe single x, the x here can be maybe a feature function. For example, it can be a first moment, second moment, or even higher moment of x. Try to match all those expectations under these two formulation. But if you only have finite number of moments, it does not necessarily yield the true density ratio, even asymptotically. So that's why we want to use kernels. So if you have a like Gaussian kernels or universal kernels, then if you have a kernel thing, instead of x, you have a kernel function here and a kernel function here. Then we can prove that if this matches, then asymptotically, this ratio is correct. And then then this problem will just reduce to a kind of opposition problem when you try to have this norm of this difference being minimized. And K here is a Gaussian kernel, which is infinite number of, it can represent infinite dimension of features.
So how many of you have worked with kernel methods before? Remember, we didn't do kernel methods in class.
Oh, we didn't do? Okay. One?
Do you want to kind of briefly explain like how the kernel is different, or what is the intuition?
So, so how many of you seen SVM? And I guess in SVM we'll have dual formulation. So the dual formulation will have. So I guess you guys should have seen this dual formulation of the SVM, and there is this. So you have dot product in the dual formulation of SVM. And then if for example, if this phi actually is your feature function, and for example, you have infinite number, the dimension of this phi goes to infinity, then computing this dot products is very time consuming and is very computationally inefficient. Then kernel function actually is the way to incorporate very high dimensional features without having a large computational burden. And then in the case, for example, in polynomial kernel, for example, if this function actually can, for example, you have kernel x equals to x1, x2, and then I'll just write it very plus x2 plus x1, x2. We can prove actually any of the polynomial, so I'll just take polynomial as an example. Any of the polynomial functions in these two variables can actually be written as two phi functions, the dot product, which I cannot derive here, but yeah, that's the conclusion. So then, if that's the case, we can prove for any polynomials, we can, in this form, we can write that in the dot product form. Then instead of writing, computing this dot product, we can just directly compute this polynomial, which is much faster than doing dot product of these two phi functions. And then in the Gaussian kernel's case, or RBF kernel's case, this is, for example, x1 minus x2 exponent. Among zero functions, minus x2. In the RBF kernel case, we can prove this is actually equivalent to two dot products of infinite number of features. So that means instead of doing infinite dimensional features dot product, we just calculate this RBF function so that you just plug in this in for example, the kernel SVM, and then it actually will represent a dot product with infinite dimensional features. Is that a good overview? I'm not sure.
I mean, think of it as like instead of selecting a parametric distribution like Gaussian and some parameter features, right? It's not. So, if you want, definitely we can go into more details, but in this context, I mean, it's mainly used so that you don't know what moments you want to select to fit, right? Instead, it's not parametric. Is that clear?
Yeah, for example, polynomial kernel is only finite number of moments. The dot product is only finite dimension. Finite dimension of feature functions dot product is polynomial. But in Gaussian case, you can prove that it represents an infinite number of dimension of features. And then in this case, we should not use finite number is not asymptotically correct, then we should use infinite number of moments. And then kernel method is the one we can use to reduce the burden of computation of the dot products. Any other questions? Okay, so this is the optimization problem, right? We want to minimize this difference between these two integral, but actually they're just the expectation of the kernel mean. Just kernel mean, not expectation, the kernel mean. And then this is called kernel mean matching. So we want to reduce the difference of these two kernel mean. So we also so that's integral is in the population case. Then in the empirical optimization case, we reduce that to using the samples we have. So we have some source samples, we have some target samples as before, but then now we want to solve this optimization problem where the first term is just the kernel mean of one distribution. For example, is the target distribution, and then the second one is the target over source, and then using the source samples to evaluate those kernel mean, and then you want to minimize the difference of these two, subject to some of the conditions. For example, you have some conditions on the beta wise. So still want to restrict the set of possible parameters. And this is a convex quadratic program. And then directly from the ratio we get from this, the beta we get from this thing is just directly the density ratio estimates. So instead of doing classification, we are directly estimate this R, this P target over P source. Any questions? So again, there is a numerical example given by the authors. So you have two Gaussians still, that you have two densities, which is very easy to get. And then the result from that numerical example is the green one is the estimated one from KMM, and the red one is the true one, just directly computed from the two Gaussians. And then one notorious thing for RBF kernel is actually the bandwidth. You need to tune it carefully. So this is mentioned that it's possible that you need to choose the Gaussian width, which is just the sigma here. In this case, this thing is something you want to choose carefully for the Gaussian kernels. And it's mentioned that a heuristic is to use the median distance between samples. So you have samples, and then you calculate the distance, and then use the median of that. But it also may fail in a multi-model case. So yeah, there's also pros and cons for this method too. But in general, it's like a more direct way to get the densities than doing classification or directly do density estimation and then do the divide thing. Yeah.
Is the Gaussian kernel the only kernel that can guarantee the asymptotic?
No.
Okay.
So there are a set of kernels called universal kernel. So Gaussian is the most used one. Yeah, I cannot give an example of the other, but yeah, usually we just use Gaussian. But there's a set of kernel function that has this property. Yeah.
But polynomial is not.
Polynomial is not of them. Yeah.
So it depends on what inductive bias you want in your system, right? Gaussian means it's smooth, right? Like these are smooth functions. And then there are others when you assume only some set of derivatives are bounded, but the others could be infinite, right? So there are different kernels for depending on what. And if it's string matching, like you have string data, there's a string kernel. So it depends on the data and it depends on the assumptions you want to make in terms of invariance or assumptions on the functions.
Yeah, and I know applications where actually polynomial kernel is better than Gaussian. So it's not necessary that Gaussian is the one you want. It can be, I think in some of the text applications, usually that polynomial is the one you want to use. So it depends on the problems. Okay. So as a summary, we mentioned that finite moment matching is not consistent, and then we want to use infinite moment matching with kernels, and then they're consistent and also computationally efficient, which we mentioned use kernel functions that you can avoid this dot product thing, and then you directly just calculate those kernels. And then you can also prove that in this case, you can get consistent. For example, this consistent proof exists for reweighting means actually means if you use this method to do this density ratio estimation, and then use this to do the reweighting. First use KMM, get the ratios, and then use reweighting in your method. There is cases that you can prove actually this reweighting method will just converge to the direct target loss minimization. So kernel parameter selection is also a problem. As we said, you need to choose the bandwidth carefully. And then a variant for the entire ratio function under general losses is also variable. So this is not our focus today, so it's fine. Yeah, so in summary, we'll talk two methods in this category. You can do classification, and then you can do KMM. Actually, there are two other ways to directly estimate the density ratio, which we're not covering here. Which are more complicated. I'll list this as the reference of this talk, the papers. So we have seen many good points of this impulse weighting, but what are the problems of the impulse weighting under covariance shift? So one problem is high variance. So we actually hear of high variance in many different places. So the high variance here means you can actually be dominated by some of the few examples with large ratios. For example, in these two cases, I have two Gaussians, for example, and then in this case, the Gaussian inside is the source, and the outside one is the target. And in this case, the two distributions just overlapped, and the solid line is the source, and dashed line is the target. And then I tagged all those data points that has relatively large density ratio. So the others actually have very small density ratio because they're actually in the overlapping space of these two distributions. And in this case, it's even more true. Like, so you want to pick the ones that the density ratio of P target or P source is relatively large. So these are the only large ones, and the others are all very small. And then in this case, you can imagine that if you weight the points like this, you can easily be dominated by those, for example, either outliers or some data point. Look at the one with 61.1, which is like a little bit far away from the middle, but that one has the largest density. And remember, reweighting examples like this, actually you're actually upsampling your data. That means you have 61 maybe that data in your distribution. You're just duplicating. It's equivalent with duplicating some of the data in your training set, right? So then that means you're duplicating all those data points in your training set. So you can be dominated by those. So that's one of the reasons why we can have high variance in impulse weighting. And also, in theory, people have proved that for impulse weighting to get very good guarantees, you need to have the second moment of these weights to be bounded, which is P target X, P source X, which is you want this to be bounded by some value. And then you can imagine this requirement actually is very difficult in reality.
I mean, if it's a moment, then it's an expectation or something, or is it just pointwise?
Yeah, it's an expectation of something.
It's expectation over the target or the source?
I think it's over the, let me see. It's over the target. I think it's over the target.
Yeah, target is.
Yeah. So, for example, you have, and this is the true one, not the estimated one. So, estimation actually can have some hard requirements to say, okay, we want our weights to be smaller than some value, and then we can use that as an inductive bias and then do our estimation. But this actually is the true one. For the true density ratio, it needs to satisfy this thing. So it's actually very hard. So that's why.
And so actually the third one about small samples is true in general, right? Like bias variance trade-off, if you recall, if you have small number of samples, the variance can overlap. Right, and this is unbiased, so importance weighting we made it unbiased estimation. So the bias is 0, but the variance.
The variance is huge. Questions? Okay. So, okay, this is the last slide for the covariance shift case. We are now switch gears to the label shift case. We have set two methods for estimating this ratio p target x over p source x. But now what we're interested in is the p target y over p source y in the label shift case. So I'll introduce this method called first proposed, I think last year. It's called the black box using class ratio estimation using black box predictor. But actually, this idea originated from many years ago. For using this kind of method to do class ratio estimation. So the first two is first we say the first two line is true is that so since we have px given y is the same, then if we have a classifier which is f, we apply that to the x variable. Then this still holds. If we just apply the same f classification to the x variables, then we'll get the first two lines. When x from source and target, then fx equals to some labels, maybe for example one of the classes in your classification. Given the true label is okay, fxy equals to y prime, which is one of the labels. Given true label is y, this distribution is the same between source and target. And then we can have the derivation like in the target distribution, the probability of our prediction, the class of a prediction is equal to one of the labels. It's equivalent to this. And then we can replace this part with this part because we know they are the same according to the label shift distribution. And then you will just get, you replace this, you use the joint distribution here, but then have this p source y equals to small y here. So you get this ratio here. So I'm not sure whether this is a good way to explain this thing.
But it's the same importance weighting principle, right?
Yeah, it's the same. This is just a way how we get this in using a f, using a classification method. So you apply the same f on the source and target samples, and then you can derive that this ratio appears here. And we can estimate both this is a confusion matrix basically, and this is actually, you just apply the predictor on the target x example and get a distribution. And this is you apply the predictor on the source data and then get the confusion matrix of your prediction and also the true labels. So these two parts you can estimate from the data using either both source and target data. And then the problem will just reduce to B equals to C times W. W is the density, is the weight. And both B and C, C is the confusion matrix, as I mentioned. B is the class distribution using your predictor on target data.
So what's the main challenge here is this density ratio now depends on Y, right? Whereas in the covariance shift you had both in the target and source. So you could just directly look at how to estimate it. The main challenge was more high dimensionality rather than you had the samples. But now you don't have P target of
Right.
Y given Y, Y equals Y, right? So you don't have the distribution of labels in the target.
Right. Yeah.
And so that's why this has to be the indirect method, right? That's the main difference. It's not, both are not equivalent. And so the question is, even if you don't have the target label, the true target label distribution, is there a way to estimate that? And rather estimate the ratio directly, right? So
Yeah.
that's the question. That's the challenge.
Yeah. Yeah, as I mentioned, like we do not have the Y's in the target, but then we can use this kind of method to indirectly, but get the weight estimated. Still, we're in this impulse weighting framework, and then so.
Do you see here, I mean, what this equation, what it's saying is f of x is now the predictor, right? So
Yeah.
now the predictor would have some probability of being correct under the target and also some probability of being correct in the source.
Yeah.
So you're relating the two. That's what that equation is saying. Because what's kind of tying the two is the common predictor, right? You have just f of x is the predictor, which was trained, and so you want to compare how correct it is both on the source and the target. And you can relate the two through that equation. Do you see the equation? I think everybody sees that the equation works, right?
So this equation is just derived in the previous slides. It's exactly the same thing as the last line here. And the way we derive it is you first write out that and then replace this from target to source, because this is, as I said, is true when you apply the same predictor to source and target data. And then this is the B and this is the C in our later slides.
And you are using the invariance of the generated distribution, right? In the previous.
Right, in the previous one, yes. Here, this step is just using using this assumption that px given y is equivalent between these two, so that after you apply the same predictor, is still equivalent.
That's the crucial thing. Right?
Yeah.
Otherwise, you wouldn't have it.
Yeah.
Okay, so you can now go back and relate it to just the source distribution, which you can evaluate, right? The confusion matrix in the source, right? So
Right.
that you can evaluate. Right, the capital C matrix is completely you can evaluate it, right? I mean, of course, you have a limited number of samples, so you have some perturbation, but you can evaluate this.
Yeah. And the B you can also evaluate because you just apply those to the target data. So both B and C you can evaluate. Then it's just a question: how do you want to get this W? Then you can get this using matrix inverse. So B is just W is just a B times C inversion, or you can solve regularized optimization problem, which is the method, which is the RLS method. So based on this equation, depending on how you want to get your W, you get different methods.
And do you see why the left-hand side you can evaluate? What does it depend on? It only depends on x, right?
Yeah.
The y prime is fixed. So it only depends on the distribution
Yeah.
of x.
You have some target data, and then we just apply those, apply this F to the target data and get this predictions. And yeah, so it only depends on X.
Because you are only applying this fixed predictor onto your target data and counting how many times it gave different labels. Right? I mean, not just counting them with the probability.
Yeah.
You see, I mean, that's how we make it tractable, right? In general, if you have to look at this ratio, both the target and the source without knowing labels in the target, it's impossible. Right, but this extra assumption of invariance of the generative model in the two makes it possible. So it's much more involved to do importance weighting here compared to the covariation.
Yeah, one reason is easy is also usually you have a finite number of, for example, the classification, even if it's 10 class, then this P, this contribution measure is 10 by 10, and then this the B is just a 10-dimension vector. So the problem here is like much smaller than, you have a high-dimensional X, and then you want to get the ratio estimated using the X. So here is things. Usually the labels are finite categories, and then the problem is like much easier. But that's not the only reason we want to do label shift. It's just the kind of byproduct of this thing. Okay. Yeah. So there are some bounds. I think we probably will skip this. Yeah. So I think I just finished the first two in this talk. As a wrap up, we talk about ID, we'll talk about distribution shift, and then there are two general methods. But in this talk, we do not have time for the second one. So we talk about ARM, doing that in ID, and more importantly, doing that in the distribution shift case, which is using imbalance weighting, and then we cover covariant and label shift, different ways to estimate density ratios or label weights, and then so in this case there's two steps. One, first you estimate the weights and then apply the weights to the method, and then maybe next lectures we'll cover the second perspective and then to compare these two perspectives. Okay, thank you.